everybody braving the weather and the schools being closed and coming out. And hopefully you had, I see a lot of you have your lunch. We do have coffee and water over here. And restrooms are down the hall this way. At the end of the hall, you'll see by our kitchen. We also have a sink and kitchen amenities out there, microwave if anybody needs one. So just help yourself. And today we have Brett Emmons and Megan Jacobson. They are with EOR. And they have been conducting work on harvesting, stormwater harvesting and reuse. And actually part of the study that they've been involved in was funded through a joint research grant program between Minnehaha Creek and the Mississippi Watershed Management Organization. So this is the result of the study that they've been conducting over the past couple of years, I think. And he'll obviously run through the results of this study. They've developed a calculator tool. And I believe also run through some case studies to help you understand how you could use this in your own work. So with that, I will turn it over. We are recording, but this is just for internal purposes. So don't worry if somebody shouts out something really strange. That's okay. We're just trying to get the kinks out of our system. And we do have one monitor over here. I apologize. It's not picking up the signal for some reason. So hopefully everybody can see through the screens that we have here. So does anybody have any questions before I turn it over just about the logistics here? We are scheduled to go to about 1:30, and Brett said that he can stay and answer some questions for a little while, and then he actually has a meeting he has to get to, but he will accommodate as much as he can. Okay?
So I'm Brett Emmons from Emmons Oliver Resources. We're a mid-sized firm that does kind of interdisciplinary water work. Our tagline is Water Ecology Community. As we figure out the logistics here, let me know if I need to move. If I'm in front of a screen, there's a couple different spots to look at. Or if you can't hear me, let me know. My background is actually originally did forest ecology, kind of an ecology background. Then I did some international work and then got back into school. Got a master's in water resource engineering, so very much a hybrid type of approach. And that's kind of the hallmark of our company, is being kind of very interdisciplinary. Megan, just introduce herself real quick, too.
Probably hold this away. I'm hearing the echo. So I'm Megan Jacobson, and like Brett, my background is in civil engineering, and then I went on to get a PhD in ecology. So I'm a water quality scientist at EOR.
Maybe just so we kind of know who's in the audience, so you all know each other, and vice versa, so we know who's here. Can we maybe just do a real quick rundown, name, kind of what organization you're from, and what kind of department or what you're representing? The end there, so maybe they'll be able to help us fill in any questions on that come up. So we're going to talk a bit about, is this kind of getting a little too loud? So stormwater capture and reuse. We want to talk about a model, a tool that we developed as part of as Leslie already mentioned, a grant that was a joint funded research grant from Mississippi WMO and Minnehaha Creek Watershed District. And part of that grant, we also looked at some kind of example sites, just very quick kind of cursory review, but then we'll also have a few sites that we've taken this in and have been designed and actually being built based on this tool. So we'll go through in the talk, just kind of talk a little bit about kind of what's the context here, what is it, why did this idea come together about having a reuse tool, and what do we look at. Part of the project was a literature review to kind of figure out what the state of the science is out there in terms of stormwater reuse. Another part of that research grant was then to develop the actual model, the tool, spreadsheet model. It's kind of a lower end model, high end tool, I guess you could consider it. And then also look at some applications, both within the grant. We did some specific just kind of test sites just to check. Basically, it was a way for us to kind of debug and make sure the model is working as we want it to, plus to kind of get some trends and ideas of what things work and what are some of the pressure points when you're trying to design a reuse system. And then since then we have a couple other examples of actual projects that we've applied it to. And then some concluding remarks, and we should have plenty of time for questions. I hope we'll see how slower we go at talking, but this is kind of nice. We often do this at I've presented this at a couple national level conferences, and it's usually, just 15 minutes. You got to really boom through it, so it kind of was liked having the ability to kind of slow down here a little bit and spend a little time. I think we're both fine if you want to ask questions as we go along. Hopefully with the time frame we have, that should be plenty of time to do that. work well. So just interrupt if you have a question as we go along. Oops, just a little delay there. So I think what's interesting to me too about this, or I think it's just worth noting, is this to me is somewhat of an old technique. There's, if you've traveled internationally or been in any kind of a third world area, you'll realize that stormwater reuse is pretty prevalent. It oftentimes is a primary water source. So I think it's something that I would look at it as kind of an old technique, rediscovered. I think a lot of the old farmhouses had, rain barrels by their downspouts. They would conserve water. So I think it's kind of interesting. We've gotten to the point now where we're looking at, we've had this potable water system developed, and it's relatively affordable. And we've kind of gone to the point now where we have this easy water at hand that we spend a lot of effort to either pump out of the river or pump out of the ground and bring through all sort of treatment processes and pipe all across town and put up into a water tower and redistribute it all again. And then a lot of times it just ends up on things like our lawns or washing a car. And we've kind of, to me, sort of the pendulum swung so far to one side that we've kind of forgotten that we have other ways to access water, and we've just kind of turned to this idea of, well, we've got this potable water system with this very good, clean, high-quality water, so let's just use that for everything. And I think we're starting to kind of step back for a lot of reasons and say, well, maybe that's not the best way to handle our stormwater, both from what the negatives are plus what the positives are of that water. I think the other thing that excites me about this that is, I think, very relevant is it's really, especially today, this convergence of a couple issues. I think, first of all, is stormwater standards are evolving. They're much more focused on the quantity, the volume of runoff, not just the rate of runoff. Old standards were often about just ramping down the rate and maybe giving a wet pond where water can settle out some of the solids, to now our thinking on stormwater has evolved to the point where we realize just all that excess water that gets created as we change land uses has its own impact. Both it carries a lot of pollutants with it, plus it carries more power and damage to our systems. So a lot of the new stormwater standards are much more looking at volume control, not just the rate control or the water quality ponds of the past. So here's an application where you can potentially start getting at that volume control, and especially in some kind of difficult situations. And I think you converge that with the idea that at this point we're looking at a system where we're starting, if you've been paying attention to the papers, and we've been involved in some of this, the question is coming up about, we've shifted over to groundwater for a lot of our suburban water sources, but is that really a sustainable use? And the studies are starting to come back, and we've seen things like White Bear Lake. This is a picture here of White Bear Lake with the old shoreline. Why it's not showing up on there? Just one of those things. Well, if you can imagine, the trees are the old shoreline of White Bear Lake, and you can see that people are trying to extend their dock out. It happens to be kind of a shallow shelf of a metro lake, but obviously this water in the lake is quite a bit lower, and it's having a pretty dramatic effect. And the more studies that are looking into this, USGS has done a lot of phase 1 study, and they're moving on to another phase. All indications are so far that the likely an exacerbating cause of this is the fact that we have very high water demand, and this lake is, a lot of our lakes in Minnesota are actually tied into that water table. That clean water that you get from the groundwater is what supports the high quality lakes. So as we start to pump on that groundwater resource, we're now starting to see that reflected in some impacts. And the predictions are, with some of the regional modeling that's been done, is this, if we just keep along this path of continuing to pump so much groundwater and continuing to emphasize the groundwater withdrawals for potable water sources, we're on a trajectory where we're going to really have some pretty severe shortages and problems show up. So I think, to me, what's also kind of interesting about this is, and part of the kind of brainchild of this whole approach to the study was to say, where can we take a look at irrigating with stormwater so that we're diminishing our potable water use, plus we're taking that water that would have normally run off downstream and been expensive to either treat or have to take care of, but actually keeping it more at the source where it can have a dual benefit. That's the simple approach to it. So just talking about, and I wanted to stop briefly and just talk about, so what was the kind of the driver behind this and us pushing forward to try to get this research grant, was this idea of, well, these new volume control standards are coming online, and that's a very important new approach, but there are sites that are difficult. If you have tight soils, if you have contaminated soils, if you have shallow bedrock, there are some sites where doing volume control can be fairly challenging. And I guess what we're finding is this is actually a new tool in that stormwater toolbox. If you can use volume, if you can use reuse, that's another way of taking stormwater out of the budget, even if you don't have infiltration as your primary way of handling the water. So I think that's a need for the tool. And I guess I think similar to talking to Cliff Eichinger here before, the thing we were running into is we have some communities like Inver Grove Heights is a community we work with that has very aggressive kind of low impact design standards, very high bar set in terms of what kind of volume control has to be set for every new development that goes in. And we started having people come to us and say, well, you know, buying our irrigation water is getting to be very expensive. What if we want to use up some of our stormwater on irrigation? We want to use that as our BMP for all these high stormwater standards you have. And our first reaction was, well, that sounds great. Yeah, I mean, I think that's a good idea. That sounds valid. But as we got back to the office and debated it, we could come up with all these scenarios of, well, but we just had a rain, so you know, how much water really gets used up in this? And kind of this idea that it's going to vary through time, and there are some limitations to the system. So it's not infinite, even though it's good in concept. It also has its limitations of how you would actually apply it. So it really felt like there's a need to put together something beyond just this concept and actually have a design tool that allows you to quantify and say, okay, if this is the way you design your system with this much storage, this kind of irrigation, this amount of green space, what is the actual annual budget of water that you've been able to take care of with your reuse system, so that we can get at that question when the developer comes in and says, well, I'm going to do X with this pond and do this irrigation area. You can say, okay, you met 75% of your volume goal, now meet the rest of it, or whatever the number is. We needed some way to quantify that. So that was a big driver behind this. It was just that problem that I think Cliff sounds like they're dealing with in Ramsey, Washington Metro watershed. So we'll jump into the literature review, and I'll let Megan take over here for a few minutes.
Of course, it's always backwards. This is my shirt. And I don't have a pocket, so I'm going to hold it. Luckily, our pointer doesn't work, so I have one less thing to hold on to. All right, so, and I have notes here, so pardon. I'm going to stick close to this table. So I'm going to share with you some results from the literature review. When we started the project, we thought, okay, let's look at, as Brett mentioned, what's the state of the science so we don't end up remaking the wheel. And we completed this in 2011. I just want to point out, this is a growing field. New documents are coming out every day. So, you know, the minute we completed it, it was new information was already available. So I'm just going to share with you some tidbits that we found, some interesting facts, and kind of, it's places that you can start to look at other programs that are out there and what issues that other states are addressing in terms of stormwater reuse and harvesting. So in our literature review, we basically ended up focusing a lot on state manuals, other programs, and so, well, except for Australia here, but there's a very advanced stormwater harvesting and reuse program in Australia, in New South Wales. We looked extensively at that. Florida, Texas, Virginia, North Carolina, Washington State were ones that had documents that were readily available for the public. At Oh, I'm too low, sorry. Brett, is louder. Is this good? Here? Okay. Yeah, that's good. Okay, and I just wanted to point out too with the states, California has a lot of programs, but it's a lot of city-based, so it was hard to keep track of. So we just kind of focused on some of these state examples. And everyone can hear me just fine now? Okay. So Brett was just wanting me to clarify, what we're looking at is there's a difference between harvesting and reuse. So harvesting is just the collection of the water. So it can come from rooftops as rainwater. It can be collecting of stormwater. And we do that every day in stormwater management. And then what we're looking at is then the reuse component. Okay, we've collected the stormwater, and then how can we reapply it onto our landscape to use it for irrigation, potable water, you know, in place of potable water demands, industrial cooling, things like that. So some of the things that looked at in terms of just the state programs were, you know, what are the program goals? So is it in the arid Southwest and they just want water conservation, or are they in a climate like Florida or, you know, the upper Midwest where we're looking more at stormwater management instead of just water conservation? So that was an important distinction. We feel like a lot of the information out there tends to be focused on that Southwest arid region, and just now we're starting to come online with the other states like Minnesota putting the application towards stormwater management. And then again, what were the water sources? So It's easier to deal with roof water since there's less nutrients, contaminants, but some programs are focused specifically on stormwater. So we were interested in those because that was our focus. And then what various reuse applications are there? I just listed a few with the municipal, industrial uses, irrigation, and we were just looking to see kind of commonalities. And pretty much every program has similar ideas for use. And then one thing we were in particular looking for is how other states are addressing the regulatory component of stormwater harvesting and reuse. So how do you give credit for the benefits you are achieving from collecting your stormwater and then applying it in some other use? And so what we found, at least in 2011, there weren't too many regulatory programs. Virginia and North Carolina had some sort of volume-based credits. Virginia and Florida then even looked towards the nutrient benefits of, reusing stormwater and the phosphorus that you would reduce. And then some of the other states, Texas gave financial incentives, but they didn't really have a credit program in place. In Washington, similar to Minnesota, reuse is part of their BMP toolbox. So there isn't what we found any well-defined regulatory credit system yet. So that's an area that's constantly developing and where Minnesota can really, I think, play a key role in the national scene. And then the last thing was just, in terms of operation maintenance, monitoring, inspection. So now we're getting into public health risks of taking stormwater that might be contaminated with metals, nutrients, bacteria, and applying it to a public space. So we're kind of looking to see what other states might have done in terms of, how often do you have to monitor water quality in these systems? How often do you inspect them? And I'll talk about this later, but really the leader in this field is Australia. And they have quite a lengthy document that is something in a future project that can be done in Minnesota, is apply that more into a cold climate stormwater management system instead of their more of a water conservation arid climate. Other things we looked at, and this was kind of giving us background information on how to develop the reuse tool, the model that we built, was things we were interested in. Climate is changing. The precipitation patterns are changing in the summer. And one of the issues with a reuse system is, does your rainfall event match with your reuse? So, if you just use an annual precipitation amount, that's great, but maybe you're capturing all this rainwater and it's all going to overflow because when you need it, it's not in your storage system. So we were just looking at what is the precipitation timing. The top figure, it's really small. It's even small on that screen. I apologize. But the x-axis is just rainfall category, so rainfall events. So I think in the middle is 1 to 2 inches, and then 2 to 3 inches. And I think it's greater than 6 inches on the far right and maybe less than a quarter on the far left. So you see those kind of brackets, and each bar is just a different year. 2001 to 2010 was just the actual Minneapolis-St. Paul Airport data I looked at. And that's just a kind of a flavor of the frequency of rainfall events. And this is cumulative, so it would account for a rainfall event that happened over a couple days or 1 or 2 days. And so the y-axis is just the number of events. And what was interesting is, I expected there'd be many 1 to 2 inch rainfall events, but actually there's quite a few 2 to 3 inch rainfall events. So when we're thinking of how we're going to size our stormwater harvesting and reuse system, it's something to keep in mind that, a 1 inch rainfall event is too small, potentially, and that we need to think of maybe sizing a little larger. Other things is, what is the stormwater runoff? What's the water quality? So what are the nutrient concentrations, metal concentrations? If we're going to reapply that, we have to have a sense of our starting point. And so we were just finding sources of data. Mississippi WMO has monitors stormwater effluent. The U of M, Pat Brzonik's lab has done a lot of stormwater water quality monitoring. And then there's the National Stormwater Quality Database online that is compiling nationally all the data. So we're just kind of listing some of those sources to get a sense of, in our stormwater harvesting system, what is the water quality that we're starting with? And that's in our report. And then along the lines of water quality then, since the goal is trying to put as much water on the landscape as you can, and if it has poor water quality, what is the effect on soils and groundwater quality? So in this part of the report, we looked more specifically at kind of the academic research. There's a lot on the East Coast looking at this and actually testing, using stormwater BMPs and putting high salt runoff, high nutrient runoff, and then measuring concentrations in the groundwater table and also just in the soils. And interestingly, there's retention in soils like you'd expect, and it is transported to the groundwater, but there were surprising results in that some of the systems, the nutrients and contaminants do flush away more quickly than they expected. So that's an area of research that is evolving and should be, looked at again in the future to see what they're coming out with. All right, and so then another component we were looking at, given this, okay, how much water can we put on the landscape? Instead of a lot of irrigation rules of thumb for how much water you should put for turf grasses based on how little water you can for water conservation. But since we're looking at this for stormwater management, we wanted to go the other end of the spectrum and what's the most you can put on without drowning your plants or having lethal toxicities of metals and nutrients. So we looked a little bit at what's out there in terms of what plants and tree species are most tolerant to water logging and salt tolerance. And I guess something interesting research we found, there was a study that they looked at 800 tree and shrubs and kind of gave a relative ranking of water logging tolerance. So that's included on a report that's citation for that, but it'd be interesting if people want to look at that. Red maple, tamaracks, and silver maples kind of popped up as what I would think are more common species here as being waterlogging tolerant, and then some of the turf grass cultivars are very waterlogging tolerant, like ryegrass, Kentucky bluegrass. And then a 2008 version of the Minnesota Stormwater Manual has pollutant tolerance of tree and plant species. So that's something, if you're looking at this in terms of what plants you might want to put in a reuse site if you're going to use capture stormwater for irrigation. And that was the focus of our study, is this irrigation reuse. That's a good source. And there's things that popped up with a high pollutant tolerance were poplars, sumacs, little blue stem. There's some MnDOT urban prairie seed mix, which makes sense, having a diverse set of plant species were tolerant. And then the last thing, yes, in terms of just the background information we were looking for was this health and environmental risks. So how are people addressing high levels of bacteria that may be present in your stormwater and then applying it to a baseball or a soccer field or something where there'd be contact with humans. And I mentioned Australia really had, I felt, the most developed kind of risk assessment framework for addressing this. And again, showed the cover. It's a long name of the document, but it's in our report, so you could find it again. It's this Australian Guidelines for Water Recycling. And they have managing health and environmental risks, and there's a phase 1 and a phase 2. They're very long documents, but the phase 2 is particular to stormwater harvesting and reuse. And so on the right, I just was giving an example. So the whole document is set up in terms of, you kind of go through this checklist of things to look for in terms of managing the risks. And that's kind of how the whole document's set up. And so they go through, the health risk assessment and management, how often should you monitor your systems if you're going to apply the stormwater into a publicly accessible field? What are the thresholds for bacteria that are, might start having a higher risk of infection? I can't think of the word. And then if you exceed those thresholds, what sort of treatment do you need, pre-treatment, before you apply it to your field? So they talk about different rates of UV, chlorination, things like that. And then they go through, just a discussion of the various types of irrigation you might have, or stormwater holding ponds, and what are the different exposure risks, which you'd probably be able to guess, but they kind of more organize that data and have a logical way of looking at that. And then they also go into environmental risk management. So that's the water logging of your plants, the salinity, high salinity in your stormwater, and any metal toxicities to your soils and plants. So that's a document that we were very intrigued with, and we didn't have, you could spend a lot of time and budget just addressing that, and that's kind of, we thought was a good starting place where professionals in the Twin Cities could refer to that document and model it for our own health and environmental risk management.
Can you give us just a quick summary of some of the conclusions, like for stormwater ponds or cisterns and levels of?
Oh, it's very specific. I couldn't give a general, but I could, if someone had a specific question, like a pond would be so many colony forming units acceptable, if you monitor every week or something, then they'd have a table, and if it exceeds that amount, then pre-treatment, and you need 10 hours of UV to get it below a certain threshold of, like, I'm making up numbers, but 10 coliforming units.
One of the nice distinctions is they really think about the source area. So if you're having roof runoff, that is, they say, okay, now you can potentially pair that with a higher end use. Take it back in a building, you could irrigate without any kind of disinfection, or you might do some minimal testing just to make sure it's not kind of a hot spot. Then as you go into more of a mingled stormwater use, where now it's coming down on the ground and maybe going across asphalt or lawn, so they kind of look at the source area. Is this in a high traffic road area? Okay, that's going to start to put you down to our lower end use. So lower quality stormwater, or you're going to need to pair it up with a certain amount of pre-treatment before it becomes used. And I think they had some that are maybe not rooftop, but fairly low risk on the ground runoff areas where you might consider it a better quality water, but I think they had some testing protocols you have to really show that you tested it to make sure it's applicable, or otherwise you have to put a disinfection in front of it.
Yeah, thanks, Brett. Yeah, and that reminds one other thing that's in that manual. Oh. They also have, I felt, one of the more extensive just summaries of stormwater water quality monitoring data. So they have, they cite many numerous studies of and giving average phosphorus concentrations, and that's stuff that we monitor. But they also have all the various metals and different monitoring results for the different sources. So roofs versus and different types of roofs, and different types of stormwater that's collected. So that was interesting to see.
Where are they coming from? We know mercury comes from the sky, bacteria come from the daily septic. What else is out there that's non-point that is in these systems?
Yeah, things I ran across that were, copper in roofs. Actually, surprising, a lot amount of copper can get into your stormwater, and that has, toxicity effects. Some of the, copper, nickel, a lot of the components of your asphalts, that wouldn't really be a point source, but they just get into your stormwater. And then, all the different nutrients, and I mean, there's
Tire wear, there's a small amount of heavy metals off the tire wear.
Brake linings, metal decomposition from cars that fall off. Miscellaneous roadway.
yeah, our transportation system.
Some fungicides can be copper or metal based. The hot spot on a trout TMDL study where we had some copper spikes, and we're theorizing. We still haven't tracked it down. We're wondering if it has more to do with the fungicide type handling. So there are various sources.
I mean, is it very common? I mean, or is it site specific enough to
I think it is really site specific, and that's kind of the whole idea of this Australian guideline is, they have this monitoring regime to kind of figure out what your baseline is, and, you have to, how much of your watershed is roadways and parking lots, and, what are your rooftops and, different land applications. So, and I think that's kind of the holdup in a lot of these systems is, there's a hesitancy to put them in place because we're worried about that, and so, monitoring for that and figuring out what you have. So I don't think we could make a rule of thumb for the entire metro region even.
I can just add something quickly. One of the things we're learning recently is that as we're monitoring ponds, to see if we can dredge them out and how we dispose of them source, you may find a lot of those are non-detectable. But over time, they accumulate and become something significant. So but it is very difficult. And it could have been during the development process, sometime during the past, there was significant runoff of a certain type of chemical. It accumulated in the pond, but now you don't detect it when you do monitoring because it's gone. So it's really difficult.
Yeah, and it gets at with a lot of these, universities doing a lot of research in retention in the soils and leaching from the soils, how long it stays there. Because you're right, you wouldn't necessarily measure it in just a grab water quality sample, but it could be building up over time, albeit very slow time scales, but it could be there. Yeah.
Wisconsin and Roger Bannerman at the Wisconsin DNR is actually doing some of the best work, I think, nationally on trying to pinpoint more source areas of metals in stormwater.
It's great just to have a discussion, so this is great. Okay, next I'll move into, since we knew we wanted to develop our own tool, we were looking at what was out there already. One, if there was a great tool, we didn't need to remake one, but then also what were the pieces, the pros and cons of each one, and what could we glean from each of the tools that are already out there. So I'll kind of go through quickly some of these tools. You could, look them, everything's available on the web. You could look for this, Google it. Florida has these stormwater rate efficiency volume curves. I was intrigued when I saw these because it's all, everything is normalized to an equivalent impervious area. So essentially their whole tool is developing the figure that you see on the screen. And what this shows, it gives on the bottom axis is runoff volume of water, so that's your watershed runoff. And again, this is inches over your equivalent impervious area, so it can be used on any site. And then the y-axis is this use rate, or your reuse rate of your collected stormwater. And then the different lines are the efficiency that you're aiming for. So if you wanted to use 100%, or well, not 100%, but 90% of collected stormwater, what rate of reuse would you need in terms to collect all this runoff you have in your basin? So that was interesting. I mean, I liked the visual nature of it, and that it would be one figure you could use. But we felt that some of the disadvantages of this process when we tried to apply it to Minnesota is it used an average runoff coefficient, so it's really hard to use across different event sizes and different sites. And then it also depends on a supplementary source of water to maintain water in your pond. So it doesn't look at any annual dynamics, right? So this would just be a very broad cursory tool, general sizing of your stormwater kind of collection system that you need to store your stormwater before you can reuse it. But that's one of the tools out there. If it's paused, maybe I need to actually press the button. Uh-oh. Do I have to press it again? Oh, I see it turned off, so it must have been on. Okay, this works just as well. I'm going to move over a little bit. The next one was out of Virginia. Now we're getting more into examples of the more spreadsheet-based and design tools. And this one, of course you can't see anything, I apologize, but it's more for sizing of cisterns for harvesting rainwater. So this actually gets more at the storage component and not the reuse component necessarily, but, well, actually it does factor in your reuse. But the box on the left is your inputs into this spreadsheet. So it's an Excel spreadsheet. Anybody can download this from the internet. You put in, what location you are within Virginia, kind of your roof area. So this is roof water focused. And then, you answer different questions about how big your irrigation area is, how often you're going to irrigate, things like that. And then it also goes through uses like for toilet flushing and things like that, and helps you calculate those. And then on the right, then it just kind of goes through the different, storm events. It has some sort of rainfall data that it is using as its assumptions and kind of gives these little figures. And the goal of this is to help calculate runoff reduction credit for their program in particular. So some of the features were nice in having these summary figures and a lot of inputs that you could answer these questions to. But again, it doesn't have any adjustment for variable rainfall data, and that's, in our mind, a key kind of issue with stormwater harvesting is, having a 5-inch rainfall event and then, not needing to irrigate for several weeks. And, what do you do with that water? And this mismatch between stormwater collection and reuse. And then it was specific to this Virginia rainwater harvesting program. The next one was out of California, and this tool was actually a similar. I saw Carolina and I thought California in my head. Thank you, Brett. That's why there's 2 of us here. North Carolina, and this one was actually a Windows-based program. It's based on, I think, a similar spreadsheet type system where they have system design, so you can specify, again, your rooftop area. This is focused on the rooftop rainwater harvesting. This has some cost benefits in it, which was nice. So, what is your cost of your water, and then, sewered water and the cost of a cistern, so you can get at, how much money are you saving by reusing rainwater versus using potable water. Another screen, then what was nice about this is you can get a little more specific on your irrigation, so you can have different irrigation rates by month. And I think you might even be able to get more specific than that. You can have this custom design, different water uses you can put in. But the output then is just, it kind of gives this, total annual water savings, and, it's very much focused on how much money you save. And they have, I think, a nitrogen component, how much nitrogen is removed by, harvesting that. But that's not as much concern in Minnesota as phosphorus is. So this system, you import a rainfall file, so you could have it, you could make your own rainfall file and import it for Minnesota. They have some standard ones for North Carolina, so that was interesting, and they have that cost benefit. But it's a little hard to modify since it's the Windows-based program. So that's a program that's out there. And then I started looking too in the academic community and trying to get at this question of this variable rainfall and when do these events happen, rainfall, how frequent and how large your rainfall events are with the timing you need for irrigation. And so I ran across another kind of spreadsheet-based model, and it has a fancy name, Stochastic Reliability Estimation Tool. Some I didn't write down, some university out east. But the interesting thing is they kind of predict in the future what your precipitation might be based on past data, and they kind of look at these bootstrapping and all sorts of statistical estimation of rainfall. But that would help get at, you could put in, the 2010 rainfall data and size your system appropriately for that year, but then, this using some sort of, statistical prediction of rainfall, you might be able to get a more system that's more appropriate for various rainfall events. I'm articulating that very clearly. But again, it's very complicated, and we couldn't incorporate something like that. But that's something that's out there. People are thinking about that. This didn't work. Show this over here. All right, and then of course, Met Council has put out a Stormwater Reuse Guide. That's just a cover image. You can find it on their website. And they also have a tool for stormwater harvesting and irrigation reuse. But this one, kind of the key components of this are more on, is your stormwater pond or cistern, how often is it empty? It's more on the efficiency, how much of your harvested stormwater can you reuse? So they have some outputs of, it's empty so many weeks of the year and things like that. And it's more of a water balance tool and doesn't get into the water quality component. But that's out there as well. And then, like I said, the minute you complete something, a new document manual comes out. So EPA has this 2012 reuse guidelines that we never ended up looking at for this project, but that's out there. And it kind of, I think, summarizes a lot of the same things that I've just told you about that's in all these other program manuals. Okay, so let's get to the reuse model that we developed. So we looked at all these previous tools and, we set out with what things we were interested in. And so what we wanted to build was a relatively simple design tool. We wanted anybody in this room just to open it and have some sort of intuitive sense of how you might use it. Some of these tools and models are kind of complicated, but we like the features of the ones that were more simple. And then we wanted to be able to incorporate this timing of rainfall. So we have our model based on actual precipitation data from the Minneapolis airport. We picked out 3 representative years, a dry, average, and a wet year from the most recent data, so it ended up being 2007, 2009, 2011. And we run it on a daily basis. And all of our kind of components of the model that I'll explain further are kind of based on every individual day. We're calculating, looking at that rainfall, looking at it didn't like that. Maybe it's because I'm holding this. You just turned it off? Oh no. Okay. Anyway, looking at previous rainfall, things like that. And then what we thought was really new and unique about our tool is that we're incorporating these nutrient benefits, and phosphorus in particular. So there's a lot of phosphorus in our stormwater. We spend a lot of money trying to mitigate lakes that are too eutrophic, reducing phosphorus in our stormwater. And so by collecting stormwater and reusing it for irrigation, we can put those nutrients on the landscape and be taken up by plants and soils. So what are the benefits that we can get from that? And then also there's an interesting side benefit of the fact that we have to store stormwater in some sort of pond or cistern, and we get sedimentation out of the water column of our particulate bound phosphorus as well. So we try to incorporate some of those very general stormwater phosphorus sedimentation equations and a phosphorus mass balance into this tool so that we can not only quantify the volume reduction benefits, but then phosphorus, which we're also very concerned with for stormwater. And that's why I helped out on the tool, if you're wondering why. A scientist is on this project and not our engineers. So the model setup, just kind of a schematic. We have impervious surfaces accounted for in the model. You can set how large those areas are. And pervious surfaces, and this is where we generate our watershed runoff. So it's a curved number-based watershed derivation. Brett, anytime I misspeak, just jump right in. So I co-developed this with another engineer in our office, Greg Grasky. We have some sort of storage facility. We model both a pond and a cistern type system. So the difference between the two would be the pond, you would have to put in your side slope and the dimensions because there's an evaporation component, and depending on the water level in your pond, the surface area is very different in your evaporation, which sometimes ends up being a very large component of the water budget changes. So we wanted to be able to account for those daily dynamics and changes in that surface area. And then we have all of our kind of inputs in terms of irrigation area and where your watershed runoff is being generated as separate, so that you could use the system, you could use the model and assume everything's kind of insulated. So your watershed is being generated from your same site that you're irrigating on. But also you could separate it if you're in a very urban, ultra-urban location. Maybe you're capturing stormwater somewhere else or from your site, but then piping it somewhere that needs more irrigation water, but they're actually hydrologically disconnected. So the water budget, and this is the same in every tool we've come across, this is nothing new, but you have your runoff, watershed runoff flow coming in, you have some sort of size of your basin, we have to set a maximum size, there's a variable storage component, and then we set a sediment storage volume that you wouldn't actively pump below that volume so that you have some sort of standing volume for your phosphorus to sediment out. It can evaporate below that level. We can't prevent that. And then you have evaporation from the pond surface if it's a pond storage system. And then you have an overflow component. If the big rain events, you exceed your storage size. And then, of course, what we visualized as our main output was this irrigation component. And then the other portion then is a phosphorus mass balance that corresponds with the water mass balance or water balance. And so we have our watershed load coming in, which is based on event mean concentrations of phosphorus in our rainfall events. that you can set as an input, and I'll show you all the inputs and outputs. You'll see where those come into play. We count for mixing residence time of the pond system. You know, if you get back-to-back rainfall events, you're going to have much less sedimentation of your phosphorus, and more of it's just going to flush right out of your system, so we try to account for that. So eventually your sedimentation component is just, you know, what fraction of your phosphorus is sedimented out based on residence time and the size of your basin. And so then you can have sediment storage. And then again, you have overflow. Some of it's just dissolved in your overflow, and you can keep track of that, and then how much is actually going onto your irrigation lawn. So this is the other thing. When I was developing this, I wanted to, you know, have it kind of visually intuitive and appealing. So this is the input screen. So irrigation is always green. The watershed stuff is always brown, and the storage system is blue. So all your inputs, you know, you get the title in the second column, and in the middle would be the cells that you can actively change. And on the right are the units. So, you know, first you would start with your irrigation, and, you know, what is the area that, you know, what sort of lawn do you have that you can irrigate, you know, however many square feet. And then how intensively do you want to irrigate? So a rule of thumb for water conservation is 1.5 inches of irrigation per week for, you know, turf grass. And we assume you're going to irrigate every other day. These are just following these rule of thumbs, and that's how our model is developed. So then, you know, 1.5 inches per week at every other day is 1/2 inch, and that would be your input. And you can change that in the model. So maybe you want to get really aggressive and, you know, let's do 1 inch every other day and see how much we can put on. Maybe you have, you know, A soils, and it's just going to infiltrate really quickly. And then you can set, we have a finite growing season, so you can start your irrigation in May and end in September. Some models can do by day. I have it by month. But again, and also this tool, we're always looking for things, you know, what's the next version, something we could add. So I was just realizing just today that, you know, maybe you could have it more specific if you wanted to start on May 15th versus May 1st in terms of irrigation, which could make a big difference. And then your watershed components, you know, how big is the area that you're generating runoff? We have 2 different percent impervious areas. One is connected and disconnected, so you can get a better sense of what is the actual, how much water is being delivered from your watershed to your storage pond. If it's a impervious surface and it flows through a pervious surface, some is going to be infiltrated and not reach your storage facility. So there's that component, and then you have the 2 different curve numbers for the disconnected and then the pervious areas. And then the bottom 2 are these concentrations of total phosphorus and dissolved. And so kind of a, you know, a default would be 410 parts per billion for total and 250 for dissolved, and that's based on the stormwater data we found for the metro area. But if you had site-specific data, you could adjust that. And then the bottom is all the, you know, the basin. You know, what's the volume, what's the storage volume, the length, the width, the side slope. You could use like an integrated side slope if you have a shelf to try to get a better sense of your volume. Because again, we model that surface area by day based on the volume. And then to switch between a cistern and pond in the model, you're essentially just turning evaporation on and off with a 1 or a 0. And then you set some sort of initial size of your basin. And our model runs 1 calendar year at a time, so it's 1 full year. So you'd have to have some sort of starting volume. So then you might be able to do that to account for some snowmelt dynamics. So if you know it's going to fill up from snowmelt, you'd start it full. Or maybe you think it's going to be empty, you can start it empty. And then the output, so what we show in the outputs, it's the annual summaries in this table. And the rainfall years are listed on the left. So we have that dry year, an average year, wet, and then we have an average of all 3. You know, assuming that these happen year after year, so what's kind of your average performance of your system. And then within each rainfall category, there's the blue rows and the orange rows. So the blue is the volume, kind of mass balance, or balance, and the orange is the phosphorus mass balance. And they show, so you get your total volume and phosphorus load from the watershed, that's that second column. And everything is kind of relative to that amount that comes in. So we have a component that goes to overflow. We have some that goes to irrigation. You have your volume that can go to evaporation for phosphorus in particular, how much is being stored in the bottom of your storage pond or cistern. And then you can account for some sort of change in storage. If it starts full and ends up empty because there was a lot of evaporation, or if it starts empty and fills up by the end of the year, you know, you don't want to say all that's going to irrigation when perhaps you just, you know, it's just in your pond or your cistern. So that's the summary screen. And that's also shown in the output as a bar graph to be a little more, you can compare between the different years and the different sources. So you have, in each figure, the top one is in terms of, you know, volume and mass, and the bottom is a percent of the watershed total. And then each of the colors is a different source. So, you know, the white in each one is a change in storage. You have evaporation in purple, irrigation is green, and your sedimentation is orange. And then if you notice on the bottom, or in all these figures, this is a system that started full and ended up empty. So you had, or no, empty and it ended full. So some of your totals are just being stored in the pond, so you get this kind of negative value, and that's all that means. So it has the capability to kind of let you know what's happening in your cistern or storage pond throughout that year. I'll have these two. And then the other thing we included is this tool can be used, or model can be used as a sizing tool as well. So you might have specific site constraints, like you want to limit your overflow, or you know, maybe there's an aesthetic component and you don't want your pond empty half of the year. You need to maintain some sort of volume that, you know, looks like you have a pond there. So in terms of, you know, your rainfall and how you want to size it, we have these annual figures to show you the water level dynamics in the pond. So what I'm showing here is on the x-axis of all these figures, it's the date, January 1st to December 31st. On the y is the, you know, the volume within your basin. And the blue line shows you the total volume you have. There's a solid line at the top that's showing you relative to the maximum volume of your pond or cistern. And there's a dashed line near the bottom that is your sediment storage volume. So you see that in this case, I think this example didn't have much watershed runoff. So we see we're losing volume through the year because we're not getting enough inputs. And you know, the minute we start using the water for irrigation, we're emptying our pond and not getting refilled. You know, so if you saw this system, okay, maybe the pond's too big. Thank you. I'm attached. And then you can see that due to evaporation, we're going below that sediment storage volume, so that could have some consequences for the phosphorus component of this system. Compare that to a different system where actually now it has a big watershed area and not a lot of uses for irrigation. So it starts out kind of half full, the basin. You can see that when we get a rainfall event, it fills up, it hits that overflow, and at the end of the year, you know, we actually filled up our basin because we just didn't have enough use for the water. So maybe this one, the watershed is just too big for our system, and maybe that's fine. But perhaps we need to look into piping the water somewhere else, or we have more water than we need. And then what we're showing in the red bars is that's the volume of your rainfall events. If you need to, you know, mitigate that downstream overflow or need to know what that will be, this kind of models how much at each rainfall event would be flushed out of your system. So that was kind of our hope with some of these figures, is that it could be useful as a design tool, that you can make those decisions, and we're not making any assumptions for the person who's actually doing the designing. So this is actually the whole input-output spreadsheet in the model, and so you can kind of see that they're all just kind of clumped together. And with that, I'll pass it back to Brett, who'll go through some examples and talk about how this has worked.
As you can see, there was a lot of background to go in there, and thanks to Megan for doing a nice job of thinking of all those pieces. Like, particularly, I thought the accounting for evaporation, I kind of felt like, well, that seems like overkill. It's a small thing, but I'm kind of glad we did, because as we got into it and looked at it, it can be up in that 15-20%. So it is enough of a variable in certain conditions that I'm glad that we had it accounted for. So I guess at this point, I was going to change over and just talk about, as part of this original project, we had kind of 7 or 8 sites that we wanted to run the tool on. So I'm going to walk you through one of those sites, just kind of see how the tool was set up and how we saw how it runs and what kind of results you get off of a given site. This was somewhat urban focused. One of our sites, though, was very suburban, a proposed new development. We had Ross Bittner on our technical advisory committee. He had a site that, before he moved up here more in the metro area, or in the inner city. He was more in a suburban community, and so he had given us a site that had been proposing to use. They had some very high standards to protect the lake, so they wanted to use reuse, and he talked about how much difficulty they had in terms of trying to come up with this kind of approach, and he said, this is the kind of tool that for designers they really need, because this really gets us at the point where everyone's comfortable. This is what they're actually going to get as far as a performance out of their system. So I'll take you through these kind of quickly, just this idea of these 8 sites that we did, and then I'll cover 2 other sites that have been designed and built or in the process of being built based on this. So here's one of our example sites from our technical advisory committee participants was this Vanilla St. Margaret campus. And you can see there were 2 small existing ponds on the site. And a lot of these we kind of constrained ourselves. We drew a boundary around the site that we were looking at, and then we more or less stayed within that boundary. And I think what's intriguing as we found running these sites, you can see opportunities where you've got a lot of impervious on the site, maybe you would want to look off-site. In this case, we had existing basins there, so we just left those existing basins. I would say they're fairly undersized by current standards, but at some point in the history, they put in some little stormwater ponds. So we just said, well, what if you just took the existing stormwater ponds and at least added this reuse part to it without doing anything else? But obviously, if you wanted to go further, you could look at trying to expand the basins. So through our exercise, we have to categorize all those different coverage types there. So the basins are kind of that striped blue. There's impervious surfaces that are designated, both the rooftop and the parking lot. And then there's pervious areas where we're going to irrigate, are that kind of green speckled. And then this actually the main football field on this campus is actually an artificial turf. So it's going to generate runoff, but it's not one of our irrigation areas. And again, as we went through this, we could have gone off-site further to the east in this park area, but we didn't really go down that path just for kind of testing the model, just to see what kind of results we got. But that's an intriguing idea as we went through this. So the output of the model was, to us, fairly interesting. I'm trying to if I have one more slide on this, or yeah. So I'll also go. That's kind of that graph. But if you just look at the inputs here, you can see we had our irrigation area, the green speckled areas. The percent impervious was 68% or 38%, sorry, impervious. Otherwise, fairly standard types of assumptions. And this is what an average year looked like in there. We've obviously run all of them, but this was just to kind of give a representation. So you can see here the overflow is that kind of darker gray at the top. The blue line is obviously the water coming into the system, and then those red bars represent the overflow water that came out of the system. So we started at about a third full, came up, and as that blue line hits the upper overflow point, that's where you can start to see runoff generated. So I guess as a designer in an average year, I might say I probably haven't pushed the system as far as I could. I'm definitely getting discharge out of it. And then I might start doing that kind of cost benefit of, well, I could add some more storage here and I could actually reduce all those overflows, reduce them in half or reduce them all together. But in this case, we were just kind of looking at this particular site and given the storage that was already handed to us at the beginning of the project. So I mean, that's kind of encouraging that this is not any additional cost for the storage in this particular case. These are the kind of opportunities we think are out there, a lot of them. So I guess using this as an example, they're 31 acres, 38% impervious, so fairly impervious, not ultra-urban by any means, but still fairly impervious, urban site. Treatment reductions, we estimated that if you had just used a typical sedimentation pond part of this, for the phosphorus, you probably would have gotten 50% reduction, and the volume of runoff, maybe a 3% reduction just from that evaporation. And this particular ones are fairly small ponds, not a big area. Whereas by adding the reuse to the system, we were able to get an 80% reduction on phosphorus throughout the average year and a 62% reduction in volume, which actually was better than I somewhat expected, I guess, for this site. Because we did have, not all the site was areas we could irrigate, but there were enough areas that we could irrigate that we could use up a fair amount of the water. So I thought that was probably one of the better scenarios of taking a site, urban site, and still being able to get some efficiency out of it, I think, by adding that component. Cliff?
In that case, was the distribution system already in place?
No, it's not. Just the ponds exist, and they had green space.
So the development's going to anticipate this, they have to do the cost of adding the distribution system, the pumping system, the regulatory control, and the ponds.
Correct. And that is another, I think, taking this one step further, we probably also, depending on where the ponds, there's definitely sites, I think, where ponds are kind of in the back area. No one really sees them. I think you can pump them fairly aggressively. If there's a spot that they feel is very high profile, that they're worried about aesthetics, you probably would temper how much you're going to pump. You'd probably pump it down to a certain spot, and then you'd stop there, maybe put your sediment storage higher so that you're not going to really drain the thing all the way to the bottom. So those kind of parameters.
Can count for that, smaller pumping volume?
Yep. So I think that was encouraging. Here's the whole, I guess if you want to see all the different various kind of scenarios. I mean, basically they're, now maybe we call them dry, average, wet. I mean, there's just basically we want to get 3 different types of years. I mean, they were different total volumes, but also you can kind of see this distribution of storms was different through each one. And then we averaged that all together to get those numbers that I showed on the overall system. So I think that was kind of nice because it also helps you just take a look at your system in a wet year and see if it's vulnerable, or a dry year, maybe you're underutilizing it. And you're right, as we looked at these various sites, we kind of felt like, okay, there are some sites that we're kind of underutilizing what we have, and then there's other sites where we would have to probably do, if we had the ability, we'd come in and change the storage or find some more irrigation area to try to make it work a little better. And so one of the things we did as part of the project too, we kind of took an example template, not necessarily a particular site, but more just kind of an example idea of a sort of a hypothetical site, and we just started running a bunch of scenarios to see what kind of feedback loop we were creating with the model. So I thought this was kind of interesting that right here we're looking at 3 graphs. The x-axis is actually the size of the pond, if you will. It's basically the volume of storage based on the inches of runoff on the site. So at the left-hand side, it's 0.51 inch of runoff for the whole site. Would be kind of, we're saying we're going to set our storage based on the amount of runoff we're trying to get to. So we go anywhere from 0.5 inches all the way up to 3 inches of runoff. And then the annual reduction that's accomplished, and this is the volume in this case. And then the 3 bars, I mean the 3 graphs are simply the volume that was irrigated, the volume that was evaporated, and then those 2 added together is the topmost graph there. And so we ran it for 3 different impervious levels because I think this was one of the interesting things we were definitely finding, kind of a very early aha moment, is that as you get up, if you're trying to figure out how much storage you need to create on your site, you're going to find out on these highly impervious sites, you really start to plateau and you're not getting much. You can keep building more and more storage, but at some point you just have no real return for that. So you're putting a lot of cost in, but you're not really getting a lot of benefit in terms of the reduction of the volume. Obviously, as you move up, so I mean, you could, on an 85% impervious site, you might be looking at 1 inch, and then beyond that, you're really kind of, you're putting a lot of cost in, but you're not really giving yourself much benefit. Whereas, you know, a 65% impervious site, that middle graph, now you're looking at, you can still be getting benefits all the way up closer to 2 inches, and then it starts to plateau. On a 30% impervious, might be more of a suburban setting, less urban, you could go all the way up to upwards of 2.5 inches before it looks like it starts to plateau. So just kind of the storage piece of this. And the next one we'll talk a little bit about, you know, the kind of the hand in glove of this is how much storage you're trying to create, but also then you have to think about, well, what's the green space that this is going to go to, because that's the other really constraining factor. And I guess that was the other bigger aha that I don't know that we totally realize on these very urban sites is really green space becomes one of your real constraining factors too. You have to have green space for this to go to. So the same thing occurs here where, again, we kept the sites fairly self-contained. So when we say it's 85% impervious, that means there's 15% pervious to irrigate. And so you can kind of look at, you can get maybe a 30% volume reduction, a little bit less than 30% on these highly impervious sites, and then you're kind of capping out. If you go to a 65% impervious site, you give yourself more irrigation green space to go to. Now you might be able to get up to somewhere of 60% volume reduction. And then if you go to more like a 30% impervious site, you could be as much as 90% volume reduction if you really maximize your system with enough green space. And sort of as we saw with some of our examples, obviously the question becomes, or the obvious point becomes, well, in those highly impervious sites, like Megan was referring to, do you have an adjacent park? Do you have some adjacent green space where you might actually be able to find more green space that your site could be tied into to be an overall benefit? So a very important point, I guess, in this kind of balancing act that you're trying to do when you're trying to reuse stormwater. And this is kind of now taking a look at the phosphorus side of that. When we ran all these different scenarios, what did we find? Well, that highly impervious site, 85% impervious, phosphorus is going to cap out not too much above what a typical pond would, about 60%. Maybe your pond would be about 50%, 55%. So very similar phosphorus benefits in this case on a highly impervious site. Whereas you go to 65% impervious site, now we jump up quite a bit. your phosphorus reduction could be slightly over 80% is kind of your maximum plateau of what you could get for phosphorus reduction. And again, a typical sedimentation pond is going to be more in that 50 to 60% range. And then in a 30% impervious watershed, if you really maximize your system of what you can do, you could get upwards of almost 95% phosphorus reduction out of that. So again, if you're comparing that to a conventional stormwater pond, these start to become pretty impressive numbers because that typically plateaus in that 50 to 60% range, and then after that, you're done. And I guess the sort of implied in this, which is also kind of interesting, is if you have dissolved phosphorus, that's something that's why ponds sort of plateau. Most of the phosphorus that you can get is attached to the sediment, and then after that, the rest of it's just getting flushed downstream. If you're in a reuse system, you can actually, that is what you're actually getting at, is that soluble phosphorus, and you're able to now treat that through a reuse kind of approach. And obviously allows you to break through that threshold and go all the way up to pretty high removals. Obviously, these are on the order of 2 to 3 inches of runoff for your site, so that is obviously a bigger size system, but that's kind of where we kind of wanted to just push the system and see where these plateau points are, these kind of diminishing return points are. So I don't know how much time I want to spend on this. I do want to leave some time for questions. These were the 8 sites that we did. Edina Country Club actually got split into 2 because we kind of ran it all together, and it's a huge green space area, and so it was one of those cases where we had way too much green space and not enough water to supply it. So we ended up kind of breaking it up to the country club part and just the golf course part. But I think we already looked at the very first one, Benilde St. Margaret, 38% impervious. Reasonable, pretty good reductions on our phosphorus and volume. And then we looked at some other Minneapolis and Edina type sites. We even looked at the Minnehaha Creek Watershed District Office. We had a 68% impervious, so highly impervious site actually for small, fairly constrained site there. That had no existing storage. We had to add a cistern, and we could get a 51% volume reduction by doing the cistern approach. So I guess a couple things I want to point out is these are somewhat urban sites, although we had a park site or 2 that we threw in here. So anywhere from maybe Vancleave Park at 14% impervious, all the way up to extremely high imperviousness, 68, 71%, in the 70%. And then that Edina Country Club was actually when we just separated just the country club site itself. And also just the volume reduction then that you can see off of this for these somewhat urban sites ranged anywhere from 40%, 46%, I guess 38 and 46, and that maybe 40% volume reduction up to 97 to 100% volume reduction if you really push that. That bottom one, that Summit Preserve from Prior Lake, that was one of those that was a suburban site where they had a very restrictive standard for a high-quality lake downstream, so they were trying to basically create a closed system with this irrigation, and we were able to kind of test that and see how it works, and they got very close to having a closed system with 97% volume reduction. They basically just proposed a very large, deep pond around some townhomes that were built around it. And the phosphorus reduction, you can see again, anywhere from in the 60% range up to 90% reduction. So it gave us a chance to try the tool, and it also gave us a chance to see how this works and kind of find some sites where, if we had more green space, that would really help. I mean, even the Minnehaha Creek office site is an example of where really what's constraining this site is probably more the access to green space than anything. If we've talked about the nursery or some other adjacent properties, maybe you'd have to find a partnership to really move that up another step. And we found sites where it was all green space and we didn't have enough water. It was kind of the reverse of that. So just quickly, 2 sites that we have applied this on. One is, it's a school site in Waconia, Minnesota. And the idea here was that there's a drainage area there's some concerns about the city wants to redo the streets and wants to add more storm sewer to this area and manage the stormwater a little better. They feel like it kind of informally runs down, picks up some of the school parking lot, and then heads down, I believe through an overland route, just combination to the Burant Lake, which has a TMDL on it. So Carver County was interested in working with the partners of the city of Waconia and the school district of Waconia and said, well, we'd like to try one of these reuse projects, and what about trying it on this site? And so we were able to use the tool to start coming up with some preliminary sizing and trade-offs. They had some kind of budget restrictions of what they could do in this first phase, but we were able to kind of give them an idea of what the performance would be for different size storage. And just the way the lay of the land was and the site constraints, this was more of a cistern kind of situation. So we were going to divert that drainage and bring it down to a storage unit right there, kind of tucked in the corner, right at the end of a dead end, next to some ball fields. And then that would be brought over to irrigate the football field. And I think one of the interesting things with not only just being able to quantify this and give them some real numbers about, well, this is how much you're going to get, this is how often it's going to, you know, how many times you're going to run out of water and how much phosphorus you're going to reduce in a very tangible way. I think what was also kind of fun and a little bit exciting about this was dealing with the grounds people at the school district, because they were just ecstatic about this idea. And I was kind of like, really, you want to cooperate with this? And we're like, well, yeah, I mean, water's very expensive for us, and we tend to not put as much water on our football field as we'd like. And so, I mean, there are times when I get, you know, prodded by people that it's kind of getting brown. And if you could give us water and it doesn't cost us an arm and a leg like the city water does, I mean, we're all for this. This is the greatest thing since sliced bread. And I was like, wow, that's nice to hear that kind of message. And I've now run across that a couple times with different developers that they're saying, you know, it's becoming, a couple of them are saying it's becoming expensive to buy water for irrigation, so that's a big deterrent. And they're also starting to see all the press articles about how the bad rap that irrigation water is getting, and they're saying, if you can give us another water source where I can diminish my irrigation, I may not take zero water off the system, but I can diminish that with a system like this, I see a big benefit to that alone. And that's kind of on one side. And then if you can tell me that I'm meeting my stormwater standard and these new standards, I'm getting a benefit there, there's actually some interest in that just from that point of view. So that was a very fun experience, just having the folks very excited there to try to reuse this water. I don't know, do you want to add anything else before I move on to this last site, the Carver County folks? Okay. Good, I didn't.
Quick question.
Yeah.
City sell water. School district is kind of governed by, I mean, do you get that resistance where we want to conserve water, but that's a source of revenue?
Mm-hmm.
I mean, does that come up? Or did that come up in this case?
Did not really come up in this case. I'm glad you brought that up, because that's another piece of this puzzle I think that's worth keeping in mind. I think there are some cities, I've heard that, kind of an initial reaction like, well, wait a second, this is kind of how we raise money. But I think there's also some communities, I think Bloomington's one, that they've actually said, I think if you think about an infrastructure of your system, it tends to happen in kind of steps. And you're finding communities that as people started getting into this kind of suburban irrigation mindset, cities were finding out that they had designed their system and they're like all of a sudden getting overtaxed. And I didn't point that graph out, but if you notice in the summer, you get these big spikes when the irrigation comes. And so from an infrastructure planner, it's kind of nice to have that fairly steady, flat kind of demand, because then you plan to that. But when we have these big spikes, now all of a sudden you're maybe having to add another water tower and add 2 or 3 more wells, and all of a sudden upgrade your entire system. And so like the city of Bloomington has actually kind of reversed the question and said, we'd like to see how aggressive we can be with our conservation measures to see whether we can just make our existing water system work the way it is, because we don't want to expend a lot of that extra capital cost to add on top of what we already had to, you know, satisfy these irrigation demands. So I think there's both at this point, but I think more people are starting to recognize this idea of some of the benefit side of it. The other one I was going to quickly mention is, again, a developer that kind of had that kind of reaction of, well, actually we see some real benefits. Inver Grove Heights is a community we've been working with for a while. They have very strict, they're basically developing in a landlocked area, so they have very strict standards. The way this was one of the last editions, and there were some kind of trade-offs and lost some storage along the way, it got to the point where we were really trying to get, it's on a fairly hilly site, kind of a challenging site to build to. They have very high, low-impact design standards. Their designer went more for a conventional curb and gutter pond approach. They could never quite meet our volume standards, which we kind of expected, and we were at this stuck point for a little while this last summer. And at some point they came forward and they said, well, this water reuse, could we use our irrigation water to meet your volume control standard? And we were like, well, that's why we built this tool. And so yes, we would like to take a look at that with you. And they were very happy with that, because it was a challenging site. It was, you know, the city had some of its concerns about trying to do rain gardens on steep hills. So that we did end up with a system that has more of a conventional looking pond down here, and then irrigation. They originally were going to do it on the county road corridor, but they decided to do it. They had some internal trails and open space within their development, that's where they're going to use the irrigation water. So it was really it's a very good example to me, I guess, where, you know, this was one tool that they actually gravitated to. They brought it forward and said, this is something we think we'd like to see. And so we were able to make sure that we had our 5-year volume control standard, which is the bar we've set fairly high, to say that, yeah, this will work. This is the right size. Given the drainage area, given the size of the basin, and given the irrigation area, we're comfortable that we'll get the kind of volume control that we need to meet our standards. We do a pre-post comparison there. Cliff?
So those would be developing, you typically wouldn't irrigate those.
In this case, yeah, we started out with road right away, which you would possibly irrigate, and then we ended up changing over. They decided they didn't want to get in with the county roads, so they ended up coming into kind of passive open space areas, right?
So in this case, they would provide a distribution system strictly to get rid of someone.
Yeah, in this case, that's probably how it's going to work. It's going to be more of a passive area. Yep.
What about areas, okay, so here's the issue we're running into.
Mhm.
We start to run around and talk to utilities folks.
Mhm.
Is, in many cases, they're going to want a redundant supply. They're
Mhm.
going to be efficient here. But you can't have two systems be tied together because now you're going to have cross-contamination. Even with DRZ, you pressurize on both ends of it, so you have to run a redundant system. How are you addressing that? Are you finding pushback on, well, that's a lot of extra cost, but now I have to run a second irrigation system?
Well, I think, I mean, to me, the sites that we've looked at is, I mean, you're right, if it's a highly visible, highly irrigation dependent kind of landscape that you've designed in, I wouldn't necessarily, I mean, you can run those graphs and see what you've got, but you might not want to just have this stormwater as your sole source, because we're not really hoarding it. We're trying to, as soon as we can, we want to get it out there and back into the soil once the storm has passed and we've got the recovery of the soil. But what we would say is you may want to add an extra source onto your reservoir. So you could just have a potable water system that comes in and adds to your reservoir that's separate from all the stormwater that comes into that reservoir. So you basically have the stormwater source and then a potable water source, and the irrigation draws off of that source. Is the way we would configure it, I guess.
So you just put a flow in there like a toilet?
Mm-hmm. Yep.
Okay.
Yep.
But what you have to be careful for with that is that if you're filling that pond up at all with the potable water, then it's not available for water for the stormwater.
Yeah, you kind of fine tune it to bring it up a little bit, use it, and then bring it back up again. Yeah, you're right. You probably wouldn't want to just fill it all the way to the top every time.
We did it with the size of the system, but we truly did it just a float valve, so that potable never goes into our system.
Mm-hmm.
It shifts, and we built the irrigation system to truly determine what the depth is.
Mm-hmm.
And then we could control those zones
Okay.
separately when they were.
Get another crossover switch in your system. Okay.
And the zones when they were pulling water, we could control separately from the cistern than when we switched back to potable.
Okay, so kind of an isolation system in your system. Good, those are great examples and great questions. It kind of ties in. It's a good transition. I'm wrapping up here. Conclusions, I guess, what we took away from this and what we're hoping coming in is we do think there's, and I think it's maybe even a little more dramatic than we expected coming in, I think there's a lot of opportunities to repurpose ponds. Because if you've ever designed a reuse system, your storage is one of the more expensive parts of it. But if you've already got a wet pond or some sort of storage device out there, you could maybe get a lot more benefit out of that, optimizing that system. It's another new tool now, I think, that's becoming very attractive to meet the new volume control standards, especially if you have difficult sites, soils, or contamination, or whatever it might be. That's the next one is kind of what's nice about it is it is suitable for those problem sites, stormwater reuse, and reducing the overall potable water supply. I mean, we're focusing more on the stormwater benefit, but we are getting some potable water supply benefit out of this as well. And in these days where I think we're all becoming very aware of that particular issue, this is a big benefit. And I think kind of as we look forward, I think we going through literature review and doing what we did with this tool, we still think there's probably a few gaps that we want to tackle, and I kind of like to open it up to others to comment on this. But for a water quality standpoint, we need to maybe think about what kind of plants are appropriate, can take the kind of urban runoff, or depending on what your source area is, what kind of water quality plant makeup makes sense. We'd like to kind of play out this a little bit more, this idea of nutrients. The nutrients that are in the stormwater theoretically are helping support these plants. We're recapturing a kind of very sustainable loop kind of system. We're recapturing those nutrients. So we'd like to be able to better quantify that, the benefits of that. And then also on this health risk side is a big issue. If you're using irrigation, depending on how open the site is to the public, looking at the health risks of that. And that is very much a new area that needs more attention. I do know Department of Health, I've been in contact with somebody. Minnesota Department of Health is very actively pursuing this because they know nationally this is a big topic that everyone's trying to tackle or everyone's interested in right now. And so I'm kind of staying in touch with her to find out where we go in Minnesota and nationally. And plants, the plant side of it, I guess I already touched on, is this tolerance to both the amount of water. Megan mentioned that, can you find plants that you could maybe push up your irrigation rate depending on the kind of plant that you have. And then also the idea that there may be plants, which there are some preliminary support for the fact that there are certain plants that are just higher water uptakers and higher ET, so they'll tend to dry out that soil a little quicker and optimize your system. The one I'm kind of been very intrigued with is along those same lines. Is I talked to some people, Bob Pitt and some people out of Villanova University that are doing this, and they do feel like that the standard rule of thumb that irrigators use for Kentucky bluegrass is probably, you could maybe go as much as 50 to 80% higher than that. Because again, they want to make sure it's lush and green, but they don't want to over apply and spend all the extra money, so they're kind of towards the, we don't want to be starving the thing of water, but we want to give it enough, but not too much because we don't pay for all the extra. And kind of we said we don't mind going over to the other side a little bit, taking as much water as the ground and the plants can handle. We don't want to kill them, but we'd be willing to put more water on because we'd like to see the stormwater used up. So I think there's some room there. We could probably shift even some of these rules of thumb over. And I think just in general, there's a lot more need for these pilot projects to be on the ground so people can actually see how this works and see that it does work. And it's always any kind of new thing comes online, everyone's kind of looking for those examples that they can learn from, so they don't have to feel like they're the first ones there. So I guess at this point, open it up for questions, and maybe on that last slide in terms of any particular needs that you feel, after we've gone through all this, is there anything you see missing, or the kind of, you already touched on that, kind of the challenges you find if you look at this as a possibility?
Question just with like the treatment levels of, whether it's UV or physical mixed media type filters, depending on the water source. Did you get too involved in that with either of these built examples? Do you know what went into the actual filtration part, the pre-treatment before it goes into irrigation?
For the passive, we're going to do just basic sedimentation. For if you have a more active landscape that people are interacting with, then you'd have to design some sort of filtration. It's in the literature review, talks about kind of what's known out there about it, but it does add another level of complexity to the system. I know that the Minnesota Plumbing Code is trying to tackle this, and there's a lot of tug and pull right now over that. I think Plumbing Code would like to be very conservative and cautious and say, well, yeah, anything has to be treated to the highest drinking standard levels. And I think other people are saying, well, can't we kind of use more of the Australia model where we tier the risk and maybe make the standard of disinfection that you need match what the source area is. And typically, UV disinfection will be a fairly inexpensive, but it does have to be a certain quality of water. If it has a lot of high sediment load, suspended sediments, then you may have to do some pre-treatment before the UV is really the appropriate disinfection.
So Garrison Hills, was that passively or was that spray irrigated? Like, what was the...
That'll be passive. And they're still finishing up the design on it, but that's what we've been talking about is passive. Questions? Somebody else had a hand up?
So, for the health risks,
Mm-hmm.
are people just looking at the bacteria aspect and not like, heavy metals or other types of pollutants? Because if I have pollutants that accumulate in my sediment and I'm not allowed to service scrub that, and it's playing on it, if I'm irrigating something over 30 years' time, when it just accumulates in soil, or is that not like a real risk?
I think that is, Megan remembers from some of the literature review, that is a real concern, that looking at besides just the bacteria, that's where kind of that plant, if we were to look at the kind of what happens in that soil, groundwater, and plant dynamic, what is the water quality side of that, how much of it's a benefit, when does it become a problem. Before we talked about heavy metals. I guess I would differentiate. Metals tend to stick to sediments quite a bit, so that's usually where you're going to find the metals is in the sediment. So we're typically taking, we've had a sedimentation area, and we're just taking the water off of it, so I don't know if the metals will be as bad, except there could be hot spots in certain areas. But it is a big area that I think that's probably the next area needs some better attention and more guidelines, exactly how to navigate through that. I think there's a way to navigate through it, but it's just not a very standardized way just yet.
Yeah, I was just wondering in terms of mitigating impacts to the quality of life with increased phosphorus levels in these ponds or heavy metal accumulation. Is that something that is of your concern, or are you mostly concerned with just the risks to humans when you
Not so much the, I guess we didn't look at the contaminants in this go-round, but in terms of the pond accumulation, the model, you can see the concentration in the pond at any given time, and it's not that different than what you'd expect in a typical stormwater. Because it is just a stormwater pond, so it's nothing, because you're pumping the phosphorus back out, and you'd be doing a dredge management cycle. So in terms of the phosphorus, it's not going to act any different, and maybe a little better. But yeah, we haven't looked at the contaminants.
What are the regulations on disposing of sediments in the system versus man-made storage facilities?
I think it would be the same as any other kind of stormwater treatment pond that we have. In some cases, we're talking about retrofitting those. Currently, if someone else has kept up on this, in the past it was typically considered kind of unregulated fill, but I think those are becoming less applicable. And I think the biggest one that kind of got on everybody's radar screen were the PAHs. There are certain coal tars that have a high proportion of PAHs, and so when people started actually testing the sediments, we started realizing there were PAHs in there. So the PCA, I think, started coming in and saying, well, we're going to require you to test your ponds and do a sweep, but I think they're mostly targeted at PAHs. And then there was this kind of legislation right behind it to say, well, maybe we better give some funding because we may have an awful lot of contaminated pond sediments that are going to be very costly to get rid of. So I think it's a little bit of a moving target right now. Everyone's kind of waking up to it. We're getting into that cycle now where a lot of these ponds need to be dredged. You know, there's starting to become more concerns about testing and regulating whether that may have to have special disposal processes, which I think is just starting to hit right now, and there is some of that. But then there's also, I think, some concern to try to find a funding source. Because I think the valid concern is that, I think what does play out in some communities is, well, if you're telling me it's going to have to be disposed of in a special contaminated landfill, well, then maybe it's just not time yet to dredge that pond. Maybe somebody else wants to add to that. But.
It's like government data.
It's a pretty.
Just a couple of observations.
Mm-hmm.
Well, we've looked at this and are continuing to look at this quite a lot.
Who's
so
we
it's
again?
interesting you look
Which
at
community are you with, or?
Pardon?
Sorry, what you said? We? Which community are you with? I forget.
Well, as a contractor, we're building more retain reuse,
Okay.
as well as coming through the bids process and looking at this as a volume control. But as we look at it, and then as a practitioner trying to get out there, a couple things we're finding out. It's interesting that you brought up with such clarity the idea that we potentially look at plant species that will allow more water loading. You know, to our great chagrin, finding the Kentucky bluegrass and the great deal of water to check most people's irrigation. Most problem we have is over irrigation and turf. But what's going to be interesting about that is that's going to be a balance of not only finding plants that will tolerate potentially that water, but that change. Because of our radical change in patterns, that plant might take that over watering for a period, but it's not going to necessarily let me just take it away for the rest of the season. That's when I may lose the plant, or vice versa. The other thing is the balance between a lot of the areas that are very attractive for this type of use of the irrigation depends on the function. So the minute I water this beyond what's optimum for the plant health, I'm probably also contributing a great deal of compaction, which is going to reduce my ability to infiltrate. It's a pretty complex issue. But having said all of that, then the other piece that we found is there isn't a lot of magic to the cistern deflection of the ponds. The magic in making these feasible is going to be in the control systems. We're finding how we get these and how we can manage these and how we can actually change the applications. And it has to be relatively easy. And we don't have that technology yet. We're still custom building that and testing that. So I hope that doesn't get lost. There's just way too many ideas that I have an automatic irrigation system and all I have to do is turn it on in the spring, blow it out in the fall, and it's one of the greatest, as we know, wasters of water that we have. And this can fall prone, same as rain barrels. Unfortunately, it became great for the plastics industry to some extent. Most just end up full in a mess. So I applaud you, truly. I'm excited about this. I think there was one just little tweak. Retain reuse can be done in the MIDS calculator. calculator, it truly is about the performance goal permit, so it's exclusively off of impervious surfaces. So the idea that this calculator can be brought in, and for the projects that we're working on, it's really been essential for us to have a calculator where we can take the overland